Hello, I'm David. I'm the coordinator of the Maths Learning Centre, and this is the revision seminar for Maths 1B. And today we're talking about Taylor series and polynomials and their errors. Bear with me, I'm going to talk a little bit about some stuff. If I'm not finished in about 20 minutes, tell me to stop and talk about something else, okay? But I think this is important. So there are three ideas that we can get from polynomials that will help, they help me to make sense of Taylor series. And so I wanted to talk about those three ideas. So idea number one goes with this graph. So this is a polynomial. It's 4 minus 2x plus 13x squared minus 10x cubed minus 2x to the 4 plus x to the 5. And what I'm going to do is I'm going to start typing it again from the lower powers, which is why I've written it in this order. So that's 4 minus 2x looks like that, plus 13x squared looks like that, minus 10x cubed looks like that. And the more and more terms we get, the closer and closer my blue one, my second one is to the original function, at least right here in the middle here. Ooh. That would be great if they were touch screens. So right in the middle there, when I'm close to 0, they match very closely, even though I haven't got all the terms yet. And even back here, it's not too bad right in the middle there when I'm very close to 1, very close to 0. So one idea from polynomials is that I don't need all the terms to be pretty close to the right answer as long as my x is small. That's one idea. Has anyone got a theory as to why that is? It's okay if you don't. Just wondering if you had one. Got a theory there? Yeah?
So if you cube or take a number smaller than 1 and bigger than 0 to the power of 5, it's a really small number, so it's only adding on like a tiny difference.
So I'm just going to repeat that for the recording. So if you've got a number that's smaller than 1 and you do like a high power of it like x to the 5, then that new answer will be really small, and so it's not going to make much difference when you add it on. How do people feel about that explanation? We've got at least one thumbs up. I'm going to take that as good. That's a pretty good explanation. I like it. And that's why you can see that it's even the closer you are to 0, the closer it is, because the less difference those bigger powers make. Excellent. That's the first thing I wanted to say. So I'm going to write that down. So with polynomials, if x is small, you don't need all the high power terms. It does make me ask a question though. A good question would be, well, can you figure out how far away the real answer is from the one that you didn't use all the terms for? So when I go back to my picture here, sure, the qx there, which has only got the first 3 terms, is pretty close when I'm between minus 0.2 and plus 0.2. But when I'm a bit further away than that, it's get less close. So can I figure out how far away the real one is without having to actually calculate the real one. Because the whole point of using just the first three terms was because it's simpler to just use the first three than to use all six. And so it would be really cool if I could figure out how far away the real one is without using all of the rest of the terms. That would be nice. If I could somehow find some way of not doing too much extra work to figure out how bad my approximation is. That would be cool. So that's just going to flag that now. Can you tell how far away the real answer is? Without calculating all the rest of the terms. There you go. That's what I'm thinking. So, that's what I'd like to know. I'm putting it on the notes there so that when I scan it, it'll be there. You don't have to copy it if you don't want. So you don't have to copy any of this if you don't want. This is a revision seminar for you. That'd be cool. I mean, obviously you're never going to find exactly how far away it is without calculating all the rest of the terms, but I could get maybe an approximate how far away it is without calculating the rest of the terms. Okay, so that's idea number one from polynomials. Idea number two doesn't have a... Does it? Just a second. Does it have a picture to go with it? I remember doing some work on this. Okay, later. So idea number two is that some things actually are polynomials, but they're not written in their expanded out form. And we can do the work of expanding brackets and stuff to figure out what the expanded out form is, but derivatives can do the same trick. So here we go. So with polynomials, derivatives can find coefficients. So that's idea number two. And it works best with an example. So my example is going to be this polynomial. So that thing is totally a polynomial. I know that if I expand it out, the biggest power will be x to the 4. It'll have x to the 4 plus other stuff. And I could do the work of doing all of the multiplications that get me the expanded out version. But I could also use derivatives to get me the same answer. And here's how I would do it. I would go, well, I know it is a polynomial, so it's got to be something like this. Something plus something x plus something x squared plus something x cubed plus something x to the 4. That's not the number e, it's just a letter e, standing in for whatever number it really is. So it's got to be something like that when I expand it out, and it should be possible to figure out what all of these coefficients are. So the first thing I notice is that the only power of 4 that happens comes from this one, so I reckon that e is going to be a 5, so that's good to know in advance now while I'm thinking about it. And the other thing I notice is that this a is the constant term, and I know that the constant term of anything happens as the y-intercept, which happens when x is 0. So I know if I sub x equals 0 into this, it should tell me what that number there is, so I might start there. All right. So p of 0 is 0 plus 2 to the 4 plus 2 times 0 minus 1 cubed. Now let's see. 2 to the 4 is 16. 5 times 16 will be the same as 10 times 8, which is 80. 80 minus 1 cubed is minus... No, just a second. I'm going to write that all down, not do the whole thing in my head. Okay, that's 80. That's minus 179. Okay, cool. But I also know that p of 0, using the other formula, I'm not going to do all of this, will come out to a, And since p of 0 is both 79 and a must be 79. So I figured out what a is. Sweet. I told you that it was derivatives that can help me figure this out. Okay, so I'm going to do the first derivative of both formulas. So p dashed, so let's see, just enough space to fit them all. So let's see, we've got a 5, it's still multiplied and it'll still be there. 4x plus 2 to the 3, and we'll have to times by the derivative of that, which is 1, so that's okay. And then this one, 3, 2x minus 1 squared, and we'll have to times by the derivative of that, which is 2. Okay. Okay, so just simplified that, you know. And let me differentiate the other one. So let's see. When we differentiate that, the a will go away. We'll just get a b. We'll have 2cx. We'll have 3dx squared. We'll have 4ex cubed. Sweet. And these are supposed to match. Okay. You're right, that one is fuzzy. The one on that side. The one on this side is much clearer. Okay, I'll look over there from now on. So we can do the same trick, because this has got like a b just sitting all on its own. So if I put 0 in for these ones, p dashed of 0 will come out to b. So if I put 0 into this, it should come out to the same answer. So put 0 in here. Now, what have we got? We've got 20 times 2 cubed plus 6 times minus 1 squared. So 2 cubed is 8. 20 times 8 would be 160. And 6 times minus 1 squared is plus 1, so 166. But on the other hand, p dashed of 0 will also be b if I sub in 0 into this. And so therefore b is 166. It's doing really well. Let's do the next one. All right. So the second derivative would be, where was I? 20, and we'll have 3x plus 2 squared. 6 times 2, 2x minus 1 to the 1. But because of the chain rule, we'll have to times by 2. Beautiful. But p double dashed x from the other formula is 2c plus 3d times 2 plus... okay. And the same trick can... the same trick can happen. The constant term here is... it's not quite just c, but I'm sure we can figure it out from there. So p double dashed of 0 from up here so we get 60, I reckon I can do this one in my head. 60 times 4 is 240, and then minus 24, so 220, 216. Interesting. Which is 6 cubed. I don't know if that's relevant, but it's just something I happen to know. And p double dash 0 up here, all of that times 0 and that times 0 will go away, we'll just get 2c. So we get 2c is 216, so c is whatever 216 divided by 2 is, which would be 108. Okay? We're nearly there. Let's do our third derivative. So third derivative of the original function, I might have to bring it down. 60 times 2x plus 2 plus 24 times 2, because that's the derivative of what's there. And the derivative of this version of the function is 2c goes away, 6d plus 24ex. Cool. The third... I didn't actually simplify that. Yeah. I really should have done that. That's 120 x plus 2, and that's 48. So what have we got? We've got 120 times 0 plus 2 plus 48. So 120 times 2 would be 240, plus another 48, 288. And p triple dash 0 is 6d. So therefore 6d is 288, and d is 288 divided by 6, which is whatever it is. Well, 24 divided by 6 would be 4, and 48 divided by 6 would be 8, I think. Well, 50 lots of 6 would be 300, and then we take off 12. Yeah, that works too. Okay, good. It's the right answer. Okay, and then my final answer I can get from the last derivative, and we're going to have trouble reading how many dashes there are, so I'm just going to put in brackets how many dashes there are, which is a traditional way of writing the fourth derivative. And so the fourth derivative would be, let's see, 120, and then the derivative of that is 1, and then the 48 will disappear. And that was outside the lecture theatre. And the fourth derivative here is 24e. And we don't even need to sub anything in because they're just constants, but just for completeness' sake. 120. So 24e is 120, and so e will be 120 divided by 24, which would be 5. Let me just check that. Dividing by 24 would be the same as dividing by 12, which would be 10, and dividing by 2. Oh, yeah, okay, cool, it works. And it was supposed to be 5, so the world is making sense. So it turns out that my polynomial is actually, what did we get? A was 79, B was 166, C was 108, D was 288, and E was 48. No, that's D. Damn it, I've done something wrong. No, reading the wrong number entirely. D was 48. And E was 5. Really not paying attention here. There we go. All right, let's just see if that works. Here's one I prepared earlier. So that red graph there is the original version, and then I've written down here, but I haven't turned it on yet, the new version that we've just calculated, and it's the same. See, see the blue one's on top of the red one. Excellent, works perfectly well. Nice. So some things to notice about what happened here. So things that happened here. Is the constant term happened when I subbed in 0, and that always happens for any polynomial anyway. And then I had to differentiate and sub in, and that told me the next one. In the next one I differentiated again and subbed in, but then I had to divide by 2. And the reason that 2 happened is because this was a 2c, and that 2c happened back here when the derivative of the x squared attached a 2 to that c. And then in the next one we ended up having to divide by 6, and that 6 happened, let's see, well, we've got a 6d here, and before it was a 3d, so we multiplied that 3 by 2 because we differentiated the x squared, and then actually that 3 happened originally because we differentiated the x cubed. So we had to divide by 6 because that 6 was the 3 of the original power times the 2, which is the next one down, technically times the 1, which is the next one down. And this 24 happened for the same reason. If you track back where the 24 came from at the very end, it came from multiplying by the power of 4, and then the 3 from the next derivative, and then the 2 from the next derivative, and that's where the 24 came from. So what happened when we calculated these things was that the coefficient of x to the n is, let's see, we had the nth derivative. We did that derivative. We had to figure out that derivative. And then we had to put in 0. And then we had to divide by all of the powers that came down when we did the derivatives. And so that was n times n minus 1 all the way down to 2, technically, which is the same number as n factorial. And that was the coefficient of x to the n. And that happened, and it would always happen for any polynomial, and this would always tell you exactly what the coefficients are, every time. Okay. I just want to go back to my picture for a second and just check that this whole using the smaller derivatives thing actually works. So let's see what happens if I start typing this. R, I suppose. Oh, let's change the color. Yeah. Let me change the color. There we go. Purple. That's nice. 79 plus 166x plus 108x squared. It's actually looking pretty good already. That's not too bad. Even up to about 0.2, that's where it was good last time. And I guess on the next one it would get even better. Looks like the cubic is the one that gives us a pretty good approximation quite close before we start thinking we've gone too far. So that's probably a good idea for later if you want to approximate things to go to the cubic. Okay, so that's idea number 2. We can figure out what the exact coefficients of a polynomial are using derivatives. Okay, and the last idea, I'm assuming that this is going well because you didn't stop me. My last idea, which I think deserves a new page. My last idea is that derivatives can help us to rewrite functions in terms of a different centre. Now, where's the beginning of this? Okay. So with polynomials, derivatives can help to rewrite in terms of the distance from a new centre. Now that might sound like something you've never done before, but you have done that without derivatives before. And so just as an example of the idea, it's like completing the square. So when you complete the square, you might have something like, a quadratic, 2x squared plus 4x plus 11, and you may use the completing the square method, which I'm not going to show you, to rewrite it like this. So what completing the square does to a quadratic is it manages to write it in terms of an x plus 1, or an x plus whatever, or an x minus whatever squared, and a constant. Okay, but what this is doing is that this is what my parabola sort of looks like. That's what this thing looks like. And this here is the position -1 where the vertex is. So I'm actually going to draw that a little more accurately. So that's my x and y axis. Come on. That's where the vertex is, which is at -1. And what we've done is we've rewritten this parabola, it's this parabola's equation, in terms of how far everything is from x from minus 1. So when we have put in 0 into this formula, it gives us 0 plus 1 because it's 1 above the negative 1. And when we put in 1 into this formula, we get 1 plus 1, which is 2, which is how far it is from the negative 1. And when we put in negative 2 into this formula, we get negative 2 plus 1 because it's 1 below the negative 1. So what we're doing when we do this formula is we're using the distance from negative 1 as our new x instead of our old x. That's the distance from negative 1. So, as long as you've chosen what your centre point is that you would like to measure from, derivatives can help you do that. The thing about completing the square is it also tells you what that centre is. The completing the square does two things. But we might be able to complete the cube or something like that, try and rewrite it in terms of a different centre. And so I'm going to do a big example of doing that. Sorry, I shouldn't have removed that. I'll leave that there and do that.
Is it not the same polynomial?
Sorry, it is the same polynomial, but I've rewritten it.
Why isn't the vertex in the same place as the first one?
The vertex of the first one is at minus 1. Because it will be minus b on 2a.
Right.
Yeah. They are the same polynomial, but worth checking that you've done it right. Okay, so I'm going to do this with a more complicated polynomial. And I'm not going to choose like any particular centre point, I'm just picking a point. Cubics do have a centre, but I'm not going to pick that, I'm just going to pick a point. So I'm going to pick x equals 1. So if I'm going to pick a new centre x equals 1, I want a new formula that's based on how far everything is from 1 instead of on just x. And so my px is going to be something like that. I would like to rewrite it so that instead of using x, I'm using x minus 1 because x minus 1 is how far the x is from 1. So this is the distance to 1, the distance from 1. Well, actually, it's not just the distance, it does include the above and below. So it will be negative if you're on the negative side of 1 and positive if you're on the positive side of 1. Okay. This is remarkably similar to the thing we just did. We can do this with derivatives in exactly the same way. So here we go. But watch closely. If I want to figure out what this number a is, I don't want to sub in 0 into this formula, because if I sub in 0 into this formula, it will give me b times negative 1 and c times negative 1 squared and d times negative 1 cubed. And so I won't be getting rid of the b and the c and the d. If I want to get rid of the b and the c and the d, I'm going to have to sub in x equals 1. Because then I'll have 1 minus 1, which is 0, 1 minus 1, which is 0 squared, and 1 minus 1, which is 0 cubed. If I want to get rid of those coefficients, I need to sub in x equals 1. So I'm going to do it explicitly this first time. And that's going to tell me what a is. So if I can figure out what p of 1 is, so let's see what p of 1 really is. It's 6 minus 5 times 1 minus 2 times 1 squared plus 3 times 1 cubed. So 6 minus 5 would be 1, minus 2 would be negative 1, plus 3 would be 2. Okay, good. And so therefore, the a I need is 2. Well, let's use derivatives the same way we did before. P dashed according to the original function. The 6 is gone. Minus 5x will become a minus 5. Minus 2 times 2x plus 3 times 3x squared, like that. Sorry, it needs to be like a mad fold-in. And then the other way of writing the derivative, because it's the same function, the a will be gone. We'll get a b times the derivative of x minus 1, which is 1. Plus c times 2. Actually, just a second. I really want to figure out what this is. Minus 5 minus 4x plus 9x squared. Okay, so we'll have a b times 1 plus c times 2 times x minus 1 to the 1 times the derivative of x minus 1, which is 1, plus d times 3, like that. And if I sub in 0, because there's a b times 1 here, no, I don't want to sub in 0, I want to make those things 0. I'm going to have to sub in 1. So p dashed of 1, according to the first one, is negative 5, negative 4 times 1, plus 9 times 1 squared, which is 0. P dashed of 1 on this one is just b, and so therefore the b is 0. And I can continue down this road. Double dashed would be negative 4 plus 9x times 2. P double dashed x from this one will be c times 2 times the derivative of x minus 1, which is 1, plus d times 3 times 2. And again, we have to sub in 1 so that this disappears. And p double dashed of 1 is c times 2. So we get c times 2 is 14, so c is 14 divided by 2, which is 7. And finally, p triple dashed x is 18. And over here it's d times 3 times 2 times the derivative of x minus 1, which is 1. So 18, oh crap. Which is 3. Okay. I was very careful to be, this time, explicit and not actually figure out what this number is as a 6 and keep it as a 3 times 2 times 1, just to make it even clearer this time that I'm dividing by 3 times 2 times 1. And if there had been a fourth power, I would have divided by 4 times 3 times 2 times 1. Okay. And so, just so we've got this, the a came out to 2, the b came out to 0, the c came out to 7, and the d came out to 3. All right. So here's one I prepared earlier. The red one is my curve, and the blue one, well, it will be blue. The one that I've turned off is the thing that we've just calculated, and yes, it is the same answer. What we've managed to do is rewrite our original polynomial in terms of how far it is from x from 1, which is this point just here. And that's not the worst thing if I only care about what happens on the right-hand side of this graph. Okay, those are the three ideas. And just let me summarise what happened there. Yeah. So the coefficient of x minus 1 to the n was Pn1, like the, yeah. Was that. Okay, so those are three ideas for polynomials. Oh, actually, just one more thing. Let's remove this last bit and see if it's any good. Yeah, not too bad. I've managed to put a neat little parabola in that curvy bit down the bottom there. And that worked not too badly. Let's just zoom in a bit and see. Yeah. Same zone, 0.2, where it's quite good. Interesting. Anyway, so I just wanted to keep pointing out that if all I wanted to do was do it near 1, then I don't really need to do up to the last power. Okay. So what we're going to do... last point. So the last point is that you know how it's only accurate when you're close to something? And the first thing that we did in step 2, the second thing that we noticed about finding coefficients, but if we only use several of them, it was only accurate near 0. Like in this step number 1, that was only accurate when I was close to 0. But if I would like it to be accurate when I'm close to 1, well, I can do this trick that I just did and convert it into something that's in terms of how far from 1 I am, and then it can be accurate in terms of how far from 1 I am. So it'd be accurate when it's close to 1 instead of when it's close to 0. Okay. So those are the 3 ideas for polynomials. And what Taylor series is saying, my function isn't a polynomial, but what if I still did this anyway? What if I went, well, if it's not a polynomial, but I can totally do this calculation. This calculation can be done. And if my function is sort of approximately looks like a polynomial, then maybe I can find a polynomial that's close enough by doing this trick. That's the idea of Taylor series. So by these ideas to any function. That's the idea. So what I'm going to do is I'm going to pretend my function is a polynomial and see what the coefficients would be if it was, by doing this trick. So I'm going to say something like f of x is whatever it is. Whatever it really is. And then I'm also going to say, well, maybe let's pretend it's also a polynomial. Where c is the number I'm using instead of my 1 that I had before, because I don't have to choose 1, I can choose whatever number I want. So I could, if I wanted to, write it as a straight up ordinary polynomial, which would be not including those c's. Or I could try and make it a polynomial based on a particular centre. And I know that both of those are possibilities of things that I could do, because I can do them to ordinary polynomials, so why not do them to all functions? And so that's my idea here. And what I'm going to say is that the coefficient of x minus c to the n is fn, the nth derivative of f with c subbed in, just like we did for our polynomial, divided by n factorial, and that n factorial is there because when you differentiate x to the minus c to the n enough times until you can sub in 0, or n, or c, when you differentiate it enough times until it's a constant, you're going to end up multiplying by all of those powers all the way down to 1. That's why this n factorial is there. That's the coefficient of x minus c to the n. And we actually call that the whole thing, including the x minus c to the n, the nth term. Like that. That is how we find a Taylor series / polynomial. Okay. So there are 2 problems. One real problem. the function you're thinking of probably really isn't a polynomial. So it's like sine x or e to the x or something. So if your function isn't a polynomial, this is not really going to work, right? Because it's not a polynomial. It will give you some coefficients, and it'll give you some terms with x minus c to the n's in them, but it's never going to be actually equal to your function, which is a problem. But that's okay, because with polynomials, if x is small, you don't need all the high power terms. So that should totally apply to all other functions too. So that's what we're going to do. Or alternatively, we'll just do it forever, and then it will be equal. So there are two alternative approaches to this not really working. So we have two choices. So choice one, do it forever, and then we say that f of x is, well, all of them forever, you know, to infinity. So there's my forever just there, that infinity. If I do it forever, let's just do all the terms. And of course we don't have to actually do it forever, because the maths will do the rest for us. Okay? So that's great. And this is called a Taylor series. So if you do it forever, it's called Taylor series. Choice two, stop. So don't do it forever. Stop at some point. So we're going to choose a specific n to stop at, and I'm going to call it capital N, because like the big N, the n that we get to. And so in that case, you call it the nth Taylor polynomial. So you have like a something like that, where an is, that's the coefficient. Okay, you can stop at some point. And at that point, you also know it's not going to be actually equal to your function anywhere other than when x is c. And so you would like to, at this point, figure out how different it is from the correct answer, and that's called the error. Do you use E or R? E. Okay, good. We used to use R for remainder. Okay, so we'll stop at some point, and this is called, now just a second, a Taylor polynomial of order n. We went up to capital N. The little n is standing for all the ones in between. Okay. And there's some more grammar that goes with this. This is called a Taylor polynomial of order n, but it belongs to your original function, and it's centered at a certain point. And so it's the Taylor polynomial of order n for the function f centered at the point C. And they don't always say centered, they might just say at. They might also say around. So and they may not say x equals c. They may just say centered at c. All right, so the important thing is that you need a preposition of location for at/around. You need a preposition that tells you where it is, and you need a preposition to tell you who it belongs to, which is the function f. Okay, and back here it works the same. There'll be a Taylor series for f at x equals c. Same sort of thing. So some people, when they tell you about a Taylor series, will say it's a Taylor series for f with c equals 2, which is completely unhelpful because, well, what is c? That only works if when you think about it, you think that this is called c. Some people, when they talk about Taylor polynomials, call this a, which is why in the Maple TA assignments they say, let a be 3. You're going, what is a? A is the centre. We have used c for centre, which makes more sense, but a is whatever. Don't be confused about that, but it is better to just tell people what the centre is by saying the centre is. Okay. Right. So these are the things that we're going to be doing. And we have to do them both. We have to do them all. Oh, and choice 2 has an extra bit. Because while, see, this one is great. We do it forever, and it's actually equal to our function. Sweet. With this one, if we stop at any point, it's not actually equal to our function. Which means that we have to figure out how different from our function it is. And so we can say, we can now ask the question of how far from the correct answer is it? And that can be that the real function is the Taylor polynomial plus the error. Like that. And this is the error. Okay, so we stop, and that means it's a Taylor polynomial, just by the way. So this is the error. Where's my blue one? Oh, there it is. But just so you know, some resources, for example, the old Maths Learning Centre resources on the website, we'll call it the remainder. Because it's the bit that remains when you take off Tn. Okay. So we would like to know what this is. And we would like to know what that is without having to calculate what f of x is. Similarly to when we did our polynomials, we would like to know how to figure out how bad our error is without actually finding the whole polynomial. Because the whole point of only doing some of the terms was so that we didn't have to do all the rest of the terms. So we'd like a way of doing that without having to calculate the actual function. And also, remember, think about this several hundred years ago when it's really, we don't have a machine that has sin x built into it, and we need to figure out what sin x is as an approximation, and we need to figure out how bad our approximation is without knowing what sin x actually is. That's what we're going to be trying to do. Okay. So while I'm at it, I'm going to put it here, but I'm not going to do it for a while. So there's this theorem, and I'll talk about this again a little later. But there's this theorem which is, I know it as Taylor's theorem, but you might know it under another name because there's another person who actually proved it. But I can't remember who that is. So there's a theorem, just a second. There's a theorem which goes that the error is this. So I'm just going to read that aloud. So the error for the nth Taylor polynomial with centre C is the n plus 1th derivative of my function with the number xi subbed into it. Some people pronounce this letter differently. It makes a x sound in Greek, so it's xi. Divided by n plus 1 factorial times x minus c to the power of n plus 1. Which is really cool because it looks very much like what you would do to get the next term of the Taylor polynomial, with one major difference, that we have a number other than c in this position here. Note that in some resources, they use the letter Z in that spot instead of the Greek letter psi. For example, in MapleTA, because you don't have a psi symbol on your keyboard. Well, you might if you have a very special keyboard. So this is Taylor's theorem. Just a second, there's one more bit here. For some psi between C and X. Okay, and this is the really tricky bit. It'll be a different psi for every X. That is an epsilon. Okay, that's the theorem that helps us to figure out what the error is without knowing how to calculate the original function. And since we don't necessarily know everything there is to know about the original function, we're probably not going to be able to figure out what the exact error is. We can just say, well, it's no more than 0.3. We're going to have to estimate how big this can be to get an idea of how big the error can possibly be. We'll get back to that. So now the rest of the seminar, the next hour, will be examples of doing all these things. Okay. All right. So I have already technically given you some examples. Oh no, just a second. Oh, I've just something. When I wrote the notes last night, I've got a big star thing here saying put this in before we do the examples. Okay, so all right. I'm going to do story number 1 first. No, I'm not. It's all right. I'll go back to that. It's not right now. It's after the first 3. Okay, sorry. Okay, so let's do the 4th order Taylor polynomial for f of x, which is going to be sin x plus cos x at x equals pi on 2. All right, just an example of figuring out a specific order Taylor polynomial. So I'm going to try and go through all of the options I can think of for how these could be arranged. I may not get to all of them. I may go over time. Just warning you, if you have to leave, I don't feel offended. It'll be on the recording. So, okay. So, to do a Taylor polynomial, I'm going to rewrite this function as if it was a polynomial. And I don't have to do all the a's and whatever. It's going to be a 4th degree polynomial. It'll go up to an x to the power of 4. Only it won't be an x, it'll be an x minus pi on 2, because that's where the centre is. And in order to find the coefficient of x minus pi on 2 to the n, I'm going to need the nth derivative of this. So I'm going to need up to the 4th derivative. All right. So the derivative of sine is cos. Derivative of cos is minus sine. Derivative of cos is minus sine. The derivative of minus sine is minus cos. This will be minus cos, minus minus. So the derivative of cos is negative sine, and so we've already got a minus, so it will be. And the 4th derivative will be sine again. Back to where we started. Nice. Okay, nice. And in order to figure out the coefficients, I'm going to need to sub in the centre to all of these. So f of pi on 2 will be sine of pi on 2 plus cos of pi on 2. Well, I might just draw a unit circle up here. Okay, sine of pi on 2 is 1, cos of pi on 2 is 0, that's 1. Okay. F dash pi on 2 so cos of pi on 2 is 0, sine of pi on 2 is 1, so we get negative 1. cos of pi on 2 is 0, sine of pi on 2 is 1, still negative 1. Minus cos of pi on 2. So cos of pi on 2 is 0, sine of pi on 2 is 1. Oh. And this is back to where we started. Cos of pi on 2, which is 1. Okay, so it looks to me the next one will be negative 1. So if we did this longer, it would be 1, minus 1, minus 1, 1, 1, minus 1, minus 1, 1, 1, minus 1, minus 1, 1, 1, if we did it forever. Okay, and then to get the actual coefficients, we're going to have to divide these by their matching factorials. Okay, so I reckon we can do it now. Taylor series 4x, Taylor polynomial number 4 will be constant term. Yeah, and do you know what? I'm just going to do the division now. Yeah. Ignore me. I need to, if I had more space, I'd do another column here, but I run out. So the first term is 1. The next coefficient is the answer I got for here divided by 1 factorial. The next coefficient is the answer I got here divided by 2 factorial. The next coefficient is the answer I got here divided by 3 factorial. Well, it won't be minus 1 by then, just 1. Divided by 3 factorial, which is a 6. And the last coefficient is this one divided by 4 factorial, which is a 24th. Okay, so the Taylor series, Taylor polynomial of degree 4 is 1. So that's minus 1, that's minus a half. 1 minus x minus pi on 2 minus a half of x minus pi on 2 squared plus a 6 of x minus pi on 2 cubed plus a 24th of x minus pi on 2 to the 4. It's tradition to use a sub whatever for coefficients, but I should probably have just said this to tell the reader that that's what I'm actually calculating when I'm writing those a's, because I haven't told the reader what the a's stand for. Okay. So, look, let's see. This is not, I haven't prepared one earlier, so I'll have to do a new blank graph. Just let me mark my axes in terms of pi. Okay. So, mark my axes in terms of pi on 2. Okay, so this function was 1 minus x minus pi on 2 minus a half of x minus pi on 2 squared. Well, it's looking pretty good already at this point. Plus a 6, x minus pi on 2 cubed. Whoa, it's doing very well. Plus a 24th of x minus pi on 2 to the 4. That's doing pretty well. It works pretty good all the way down to 0 and about up to what? That's 7 pi on 8. That's pretty good for that thing. And each term got me a little bit more accuracy, but not much more when I'm pretty close to the centre. You might also notice that the fractions in front of the powers there keep getting smaller and smaller. So a lot of Taylor series do that. So it's not just your observation that if the thing inside the bracket there is close to 0, then a high power of it will be almost 0. It's also that there's really small fractions in front of them, so they're even smaller. the later powers. And that often happens with things like sine and stuff. Okay. All right. Let's do the nth term of the Taylor series for, oh yeah, thank you. It's actually really hard work as a lecturer to maintain the video camera on the thing that you're talking about. Yes. So the nth term of the Taylor series 4, I need to pick a function. On my notes, I just have an empty box here to fill in when I get there. I'm going to talk about that. For let's call it a different letter, just to have some fun. Just give me a second. Yep, that's my function. E to the 6x minus 3. 6x minus 3 up in the power. At x equals a half. Yeah, let's make it fun. Okay. So this time it's talking about a Taylor series. It's technically not the nth term because the first term is the 0th term. It's the term that goes with the nth power, which is the next one. Anyway, ignore that. It's a Taylor series, which means it goes on forever. And what they want me to do is tell them a formula for what term n is in terms of the number n. That's what this question is asking me to do. And in order to do that, I'm going to need to figure out a formula for the nth derivative of this function. Okay. So f of, it's called g. So g of x is e to the 6x minus 3. G dashed x. Well, when you differentiate exponentials, they stay the same, but I'll have to multiply by the derivative of this. Okay. We'll need another 6. So they'll still be there, and we'll get another 6. And just to be absolutely certain they're still there, we'll get another 6. Sweet. So it looks like the nth derivative has n 6s. So the first derivative has 1 6, the second derivative has 2 6s, the third derivative has 3 6s, the fourth derivative has 4 6s. So it looks like gnx has n 6s. Okay? And so therefore, I need to figure out, to find the coefficient of the nth term, I'm going to need to sub in the centre. So I need to sub in the x equals a half. Oh, look. It's almost as if I set it up that way. A good what-if question at this point would be, well, what if it didn't come out to be e to the 0, which is 1, and you just leave e to the whatever in your formula? That would just be it. Okay. And so the nth term is, so the nth term will be gn half divided by n factorial times x minus a half to the n, which is 6 to the n over n factorial, x minus a half to the n. And that's what it is. I need to do another one of these. All right. Oh, this. No, I don't want to do that. That's yeah, that's what I'm thinking. Yeah, that'll work. All right, so the nth term of the Taylor series for h of x, which is ln of 2x minus 4 at x equals 2. No, not at x equals 2. That's going to be bad. Damn it. Gosh, I'm silly. Give me a minute. I'm going to make that a 5. Right. Making it very convenient on myself. So, oh, just a second. This is going to be awful, isn't it? Give me a moment. Nah, I'm going to just ignore me. Right. Yep. Right. Good. Sorry, I was trying to make it too complicated. Aren't you lucky your exam is isn't write a question you think you can solve and solve it? Though I would love to write an exam that was like that. You know, extra points for difficulty, even if you don't finish it. Okay. So I need the nth derivative. So this will be 1 over 2x times 2, which is just 1 over x. Yay! I really should have put a plus 1 in there, shouldn't I? Oh. Yeah, I'm going to put a plus 1 in there. Sorry, guys. All right. Okay, so the derivative is 2x plus 1 times the derivative of the inside, which is 2. And I'm about to differentiate this, so I reckon it's going to be easier for me to do that. Okay, and the next derivative, so the 2 will still be there, the minus 1 will come down, and that'll be a minus 2, and then I'll have to multiply by another 2, which I'm going to put over here because I reckon it will be useful to keep them together. So the 2 and the minus 1 will still be there, and then this will become a minus 2, 2x plus 1 to the minus 3, and I'll have to multiply by the derivative of that, which is 2, and we'll get another one. Okay. I think I can see what's going on now, but I'm just going to need a bit of one more to be sure. So we've still got the 2 times 2 times 2, we've got a minus 1, we've got a minus 2, we've got a minus 3, 2x plus 1 to the minus 4, and the derivative of this is 2, which will end up there. Okay, so I can see we've got 1 2 here, and 2 2's here, and 3 2's here, and 4 2's here. So the fourth derivative has 4 2's, the third derivative has 3 2's, the nth derivative should have n 2's. And it's not called f. Okay. All right, so what can I see here? I can see a 1 and a 1 and a 2 and a 1 and a 2 and a 3. The next one would have a minus 4. Okay, so it looks like we've got a 1 times 2 times 3 times 4 sort of situation. That's a factorial. So ignoring the minuses, the fourth derivative had a 3 factorial. the third derivative had a 2 factorial, the second derivative had a 1 factorial, so it looks like we've got 1 less than the number we're up to factorial. But to do that I ignored the minuses, so if I pulled out, because this could really be a -1 times -1 times 2 and a -1 times 3. So we have a -1 times another -1 times another -1. So that's 3 -1s, 2 -1s, 1 -1. So it looks like we have -1 to the n minus 1. Now let's just check that. -1, -2, -3. That's 3 -1s, 4, 1 less than that is the n minus 1. Yes, okay. And then we still have a 2x plus 1. And then this 4 is the same as that number. This is the same as that number, so it's that. Okay, so I have my nth derivative. Of course, if I was doing that in an exam, it would not take me that long to do because I wouldn't be explaining it aloud in my exam. That would be bad. But that's the reasoning I'm going through. A lot of people figure out whether it's positive or negative and sort of make a guess it has to be -1 to the power of something, but I like to just count how many minuses 1s there are because it tells me what -1 to the power it is. So you will notice that some solutions will have a +1 in this position, and that's because they did it by just figuring out whether it's positive or negative, and they needed to, because we have an even number for 4 and it came out to be negative, we had to go up to the next odd number, and that's why they put it up. But I just count how many -1s there are because it's a little easier for me to cope with. Okay, haven't quite got the nth term yet. So let's see, hn of 1 is 2 to the n minus 1 factorial -1 to the n minus 1, 2 times 1 plus 1 to the negative n. So 2 to the n minus 1 factorial -1 to the n minus 1, 3 to the minus n. Of course, it's going to be quite different for the first one, like for n equals 0, before we did the derivative. So we're going to have to treat that one separately because this one doesn't fit the pattern that all the other ones fit. So I'm just going to keep that into account. So that's when n is greater than or equal to 1. And h of 1 I'm going to have to figure out separately, ln of 2 times 1 plus 1, which is ln 3. Which is sad, because the whole point of this was to figure out what ln of something is, and the only way to know it is to know what ln of 3 is, but we'll ignore that. Okay, so let's see. I'm not up to my nth term yet, is it? The nth coefficient for n greater than or equal to 1 will be hn1 over n factorial, which will be 2 to the n minus 1 factorial minus 1 to the n minus 1, 3 to the minus n over n factorial. Okay. And I've got a factorial on the top and the bottom. It should be possible to cancel some of it out. So lots of people by this stage of Maths 1B have just got a rule that they follow that tells them that the n minus 1 factorial on the top and n factorial on the bottom cancel to just give an n on the bottom. But I'm going to put the reasoning in for that. So there's two types of reasoning. Here's one of them, the one that I like the most. So n factorial is n times n minus 1 times n minus 2 all the way down to 1. And this bit is n minus 1 factorial. And so therefore, if I go n factorial divided by n minus 1 factorial, it should be n. And so this is equal to 2 to the n minus 1 to the n minus 1, 3 to the minus n over n. I probably don't need the brackets around the 3, I'll just keep copying it from the line above. So if you wanted to, you could probably simplify this just a little more and put that's like a 2/3 to the n, but this is fine. And so therefore, the nth term for n greater than 1 is I'm going to rearrange it because it's traditional to have the negative ones at the front. What was the centre? 1? Right. The 0th term is ln3. So, all right. So some questions will ask you for the nth term and to write out the first few. So I'm just going to do that now just to make sure I'm doing this right. So h of x. The first one was ln3. That was the one that went with the 0th, with no derivatives. And then the next one, minus 1 to the 1 minus 1, so that's minus 1 to the 0, which is 1, 2 to the 0, 3 to the minus 0, which is 1, n is 1, so it's just 1. Minus 1 to the 1. Oh, it's 2 to the 1, you're right, 2 to the 1. You're well done. N is 1. That was a 0. 2 to the 1 is 2. 3 to the minus 1 is a third. So we get a 2/3, and that's a 1. So we get 2/3. X minus 1 to the 1. And then when n is 2, we get a minus. 2 squared would be 4. 3 squared would be 9, which is 4/9. But the n is a 2. And I'll just do that many. So we end up with 2/9. Interesting. Yes?
There's a problem about cancelling out the factorials.
Mm-hmm.
So for the first term, you got a 0 under the thing. So you divide them by 0. For the first
Well, 0 factorial is 1.
Yes, but you cancel it out. So it becomes n and n.
Here. Oh, this first term?
Yes.
Yeah, I didn't do it for the first time because I knew it would be a problem. So, good noticing. This thing with the cancelling out the factorials, that's not going to work with n equals 0. So, good noticing. So you just
I can do it without doing cancel.
you just do it separately. In fact, this formula with the factorials didn't even apply for the first one. It was just ln3 for the 0th one. Sorry. So back here, I noticed back here. I said back here this only applied when n was greater than or equal to 1 because this pattern that I used to get it didn't start till the first derivative. And it was different when I was back at the original function. Yeah. Presumably, if I had, there are some functions where the pattern doesn't start till like the third or fourth one. But I can't think of any of those. Right? So supposedly the integral of ln 2x plus 1. Okay. How are we doing? Okay. Right. Now let me talk about errors. Yeah. I could talk about doing errors in a general sort of way and give you a procedure, but it's really hard for me to describe in words that are general. So it's much easier for me to talk about how to deal with errors by doing several examples. So that's what I'm going to do. And what you're going to need to do is, and I'll try and do along with you when I'm doing the seminar, is to pick out the important bits of what happened so that you can replicate those. And so that you can help you think about things. But we're going to go back to just the formula for errors here. And all the information we need is there. And importantly, this here. Okay. While I'm at it, I may just teach you how I write a lowercase psi, because that's a good thing to have learned how to do. The capital psi is 3 lines. That's the capital psi. And the lowercase psi connects them up. That's how I draw a lowercase psi. So you'll notice me starting with a tick and going 1, 2, 3. There you go, in case you're wondering. Most people are proud of being able to write a psi, which is why they choose to use it in their maths. Of course, if you're typing, it really doesn't matter. Okay, so I'm going to do this by example. So, okay. Okay. Find an upper bound for the absolute error in Taylor polynomial number 3 at 0.1 for sine x at x equals 0. Okay. 3, do I want 3? Do I want sine? No, I don't want sine. Just bear with me. I need to think of something. Let's do sine and we'll see what happens. Okay. Okay. So, all right. So I need to find an upper bound for the absolute error. And when I say absolute error, that means the absolute value of the error. Because the error could be positive or negative depending on whether the Taylor polynomial is above or below the correct answer. And so I'm just going to do the absolute value of that. Okay. And I need to first find what T3 is. I mean, I don't technically need to find what T3 is to do this, but the formula for the error uses the next derivative after the one that I used to get T3. So I'm going to have to do all the derivatives to get there. So I'm going to need to give this a name so that I can do derivatives of it. And I'll need to do derivatives. And I'll need to, because it's T3, I need to go to the third derivative. Okay. Yeah, I knew that would be a problem. Can I? Well, yeah, it'll be fine. Yes. Okay. Good. So I'll need the third derivative. And these things, if I subbed in x equals 0, would allow me to calculate the coefficients of T3. And then I would need the next derivative to find the error. So I'm just going to put that in. This is what I'm thinking. These are used to find T3 of x. Okay? But I haven't been asked to tell the reader, like the person who asked me this question, I haven't been asked to tell them what T3 of x actually is, so I'm not going to do that part. Okay, so I would use these to find T3, but I don't need to do that because I wasn't asked to. So then the error uses the next derivative. Which is sine x again. Okay. Should have done sine 2x. Yeah, that would have been better. But anyway, it's too late now. So, well, it's not, but I'm not going to do that to you. I need the fourth derivative. And my error is going to use the fourth derivative because I was doing T3 and it's always n plus 1. I'll need the fourth factorial and I'll need the x minus 0 to the 4. So this looks like I'm going to have the error for the fourth Taylor polynomial at the point x is going to be sine of... Oh, damn it. See, I still get it wrong even though I taught you how. Okay, so I take the fourth derivative and I put the letter psi in it instead, and then I divide by the 4 factorial and do the power of 4. Okay. So that means that, so this is telling me that if I pick different x's, each of them would have a psi of their own, and each of those I could figure out what the error is. And so I only want 0.1. The psi doesn't change. I mean, it will be a different psi than for other x's, but I still don't know what psi is. I just know that the letter psi is somewhere between 0 and 0.1. So it's between the centre and the x that I'm thinking of. Okay. Okay. Great. Okay. So, all right. This is unsatisfying because I don't know what psi is. So I need to pick a number for psi that I know will definitely make this error too big. Because worst case scenario is that the error is big. And so if I can say, well, I don't know what it is, but it's definitely less than like 0.03. So that's what I'm going to have to do. So, okay, so I need to think about all the psi's between 0 and 0.1 and find the minimum of those. But that's going to require me to know what sine of 0.1 was, which is what I'm trying to estimate anyway. Oh, it's all like circular reasoning. Well, I know that sine is definitely less than 1. That's not a particularly good estimate, but then the sine of anything is always less than 1. So it's totally true that E4 of 0.1 is less than 1 over 4 factorial times 0.1 to the 4. Since sine of psi is less than 1. Totally has to be less than that. I mean, that's a really bad estimate. Sine of 0.1 has got to be way smaller than that. And so I could probably even say it's less than a half, or even an eighth probably, but whatever. It's going to run with that. It's definitely less than 1. And so that would be 24 times 10 to the minus 4. There you go. It's in nice scientific notation and everything. Five? It totally is 1 over 24. Yeah, that's just David being stupid. This is where I'd probably ask a machine to help me. 1 over 25 would be 4%, so 0.04. So 0.04 and then another several zeros. Something like that. This is where I'm going to ask a machine to help me because I just want to make sure. One, 2, 3, 4, 5. Ah, damn it. Okay. There you go. Close enough. So if I use the third Taylor polynomial for sine x at x equals 0, at x equals 0.1, centered at x equals 0, and I use it on the number x equals 0.1, the answer I get from that third Taylor polynomial will be within that of the correct answer. So I could, if I wanted to, now figure out what T3 of 0.1 actually is, and it should be rounded off to the, the whatever decimal place would be the same as sine of 0.1.
How did you know you needed sine of 0.1 and not sine of 0 or sine of 0.03?
I needed 0. What do you mean 0.1?
How did you know you were doing sine of 0.1?
So it's T3 of 0.1. That's the x I'm thinking of there. So
Psi can be anywhere between 0 and that, right?
Sorry? Oh, the letter psi. Yes, the letter psi could be anywhere between 0 and 0.1. And I just knew that sine was always less than 1, no matter what. Now, that's a special case. We know a lot about the function sine, and it's always less than 1 no matter what. And so you can always get an upper bound by just sticking 1 instead of anything that says sine of anything. But for most functions, you want to pick a psi based on reasoning about stuff, which means I need an example of doing that. And this is where my limit of my examples that I'd already chosen are. So I need to now find one of that type.
If it were constant, would be...
I mean, it's still less than 1.
Yeah, you get a really good estimate, right?
Yeah. So let's do a what if here. What if I forgot that sine was always less than 1? No, that's bad. I want to pick something that I actually can do. Give me a second. So same problem, but new function. Yep, that will do. So I'm going to find an upper bound for the error in T4 of 1.3. So the fourth order Taylor polynomial at the x equals 1.3 for ln x at x equals 1. That's the center. I might even say around. Because this sounds like an at, and that, so just, yeah. Okay. That looks like just a random squiggle. Okay, so I'm going to need to find if I want the Taylor series, Taylor polynomial, I'll need the fourth derivative, and the error will need the next derivative. So let's say f of x is ln x. Dashed x is 1 over x, which is x to the minus 1. Minus 2. It's minus 3. Will be minus 4. And f Now, I had to actually concentrate extremely hard to figure out what these numbers are, because when I'm doing Taylor polynomials, I'm so used to not multiplying them together so that I can see where the factorials are. Because normally I'd go 2 times 3 and then 2 times 3 times 4. Okay, so these ones would be used to find T4 of x, which we're not doing because we weren't asked to do. And that one's going to be used to find the error, because it's the next one. Okay, so the error will be the next derivative evaluated at some letter psi. All right, so let's just write that down. The error at number 5 of x will be the fifth derivative. No, it's not 5, it's 4. The error belongs to the fourth Taylor polynomial, so it's E4, but it uses the fifth derivative. I may have to go back and change this. That's not E4 here, that's actually E3. Sorry about that, everybody. Right. It's not labelled by the power you use, it's labelled by the Taylor polynomial it belongs to. So this error belongs to Taylor polynomial number 4, so it's E4, but it uses the fifth derivative. Okay, so the centre was 1, wasn't it? Yeah, okay. All right. Now, we do have that. We can sub the psi into this. This will be... Damn it, not that. Will be 24 to the minus 5. Like that. Okay. So 24 is 1 times 2 times 3 times 4, which are all involved in the 5 factorial, so we can make this even better. That is crap. So that's 120, and that cancels with most of the 24 to leave me with a 5. The negative power puts it down here, and so I get that. Okay. So I want the error when x was 1.3. So E4 of 1.3 is 1 over 5. See, look, my handwriting's so bad, no one really should care, but I care. That's what we have. That's where we're up to. Okay. So we would like so that's, there is a letter psi, so we could say for between 1 and 1.3. So the centre was 1 and the x was 1.3. Okay, so there is a psi somewhere between 1 and 1.3 that is the correct answer for this. I don't know which one it is. So what I could think is of, well, let's choose all the possible psi's, somewhere between 1 and 1.3, and whichever is the biggest, the error has to be less than that. So, all right, well, I'm just going to imagine here. There's 1, there's 1.3. 1 over 5, the 5 isn't going to make a difference to where the maximum is. That's not going to make a difference to where the maximum is. This is. And 1 over x to the 1 over psi to the 5 goes down like that as x increases. Okay, so the biggest answer that this 1 over psi to the 5 could be is over here when psi is 1. But I can also reason that out. I'm dividing by this number, so the bigger that number is, the smaller the answer is going to be. So out of all of the choices that I could choose for psi, the one that gives me the biggest answer is when psi is the smallest it can be, which is 1. So the largest possible calculation, let's say result, is when psi is 1. And so the error will be less than this. Because I've chosen the psi to be 1, saying, well, the largest possible result is when psi is 1, so the actual error has got to be less than that, which is whatever it is. At least 5 decimal places. .3 to the 5 divided by 5. 0.123. Oh, all right, not 5 decimal places, only 3 decimal places. There you go. So it's at least that good. If I use the fifth Taylor polynomial, the fourth Taylor polynomial, and I use 1.3 center 1, then I get that. So that choice of the psi is based on that sort of reasoning. Going, well, the largest possible result happens when psi is equal to this number. I would choose psi to be that number, and then I know it's got to be less than that. And it's actually a really useful thing to include this line in your working, so that you're always actually using that reasoning. Because we don't really know what psi is. So back in the previous question, I just avoided the issue entirely and just went, oh, I don't know what psi could be, but I do know that sine is always less than 1, so I'm just going to use that number. So you don't actually have to be as precise as we were being just here. You say, well, that's always less than 1, so I'll just use 1. And we could have been more precise back here with saying, well, if x is less than 0.1, well, I know that sine's increasing on that zone, and so I could just pick a decent number that is going to work. And so I could have chosen a half for the other one, which would have been probably better. Okay. Now, are they all the issue? No. Okay. So what we have so far is choosing the psi and making sure we're using the correct derivative. One of the classic things you're asked to do is to say, well, just a second, what if I didn't tell you exactly which Taylor polynomial it was, and you had to figure out which Taylor polynomial to use to get the accuracy you want? So I might even continue this one. Continued. Use Tnx to approximate, what did I say it was? What was this function, ln? Ln 1.5. What does n need to be to get, I don't know, 6 decimal places of accuracy? Okay. So the reason I've done the same one is so that I can reuse some of the working. Okay. So we're going to use Tn of 1.5 to approximate ln of 1.5. And we need to figure out what the right n to choose to get 6 decimal places of accuracy. So I've got all these things that have to work together, but I definitely need to calculate an error because I'm figuring out how accurate I am. I don't have to actually find the Taylor. So it does look like an instruction to use that to approximate that, so I'm just going to change it. Suppose we used that to approximate that, and then we technically don't have to calculate that at all. But if you had time in the exam, I'd do it just in case. Because sometimes grammar is not a good enough indication of what the lecturer actually wants, because we all make mistakes. So I want to figure out what the n has to be, which means I'd need a formula for the error in terms of the n that I'm up to. So I'm going to need to find the nth derivative. And actually I'm going to need to find the n plus 1th derivative. So what did we have before? We had f of x was ln x. Center x equals 1. Sorry, I need to say the center. You can't do a Taylor polynomial unless you know what the center is. And then you could just pick your center to be 1.5 and you don't need any, because then it'll be exactly correct. All right, so this was our original. That's 1 over x, which was x to the minus 1. F double dashed x was minus 1 x to the minus 2. f triple dashed x was minus 1 times minus 2 times x minus 3. The fourth one was minus 1 times minus 2 times minus 3, x to the minus 4. And the fifth one, we'll do the fifth one just. Okay, so from here we need to figure out what a formula is for the nth derivative, because I need that to get the nth Taylor polynomial, which means I'm going to need the next one to get my error, because it's always the one after that. So let's see. All right, so we're building up a factorial here. We've got 1, 2, and 1, 2, 3, and 1, 2, 3, 4. So we've got a 4 factorial when it was 5, a 3 factorial when it was 4. So we've got an n minus 1 factorial. Pardon me. We have a 1, 2, 3, 4 minus 1s when it was 5. 4 gave me 3 minus 1s. 3 gave me 2 minus 1s. So it's 1 less minus 1 than the number I'm up to. Crap, these are supposed to be capital N's. Feel free to use a small n if you prefer. But if they use a big N in the question, you do as well. Need to, probably. And then it's x to the minus, and this number matches that number. Okay. All right, so at this point, this is what I would use to do the Taylor polynomial. I know I don't need this working, but it makes me feel better. So I need the next derivative to find the error. And, well, I'll just sub in n plus 1 into the formula instead of n. So n plus 1 minus 1 is n. Minus 1 is still minus 1. N minus 1 plus n plus 1 instead of n minus 1 would be n. And then I have an n plus 1 minus n instead of an n there. Extremely important when you replace an n that's got a minus next to it to use brackets, because otherwise you would have put minus n minus 1. Like you would have put minus n plus 1. Like, don't write this, because that's minus n then plus 1. You need to go minus the whole thing. It's a very common mistake. That's why I mention it, because I do it all the time. So my error in the nth Taylor polynomial will be the nth derivative evaluated at some unknown number psi divided by n plus 1 factorial times x minus 1 to the n plus 1. And this was n factorial minus 1 to the n psi. So that's this goes here, but with a psi in it instead of an x. Okay, and that is, okay, so n plus 1 factorial has all of the n factorials in it and also an n plus 1. So that's going to cancel with most of this and leave an n plus 1, like that. So let's see, we've got minus 1 to the n. Okay. And we only care about the absolute value of the error, so I might do that now. So minus 1 to the n, well, sometimes it's positive, sometimes it's negative, but either, if you do the absolute value, it'll always be 1 anyway, so I can just ignore that bit. Okay. So for some psi between the x and 1, I suppose this will have an absolute value on it too now, because I did the absolute value of everything. So the absolute value of the minus 1 to the n is 1. The absolute value of this has an absolute value. The absolute value of this is, well, it's a positive number anyway. And the number of psi's between 1, we don't know. So, no, the number of psi's between 1 and 1.5, and so it's positive. Okay, good. Okay. Oh, and the x is 1.5, so probably didn't even need the absolute values there anyway. So let's see, just for the final thing, 0.5. Oh, and that's what we have. For some between 1 and 1.5. Don't be fooled and use this number. So lots of people would say it's between 1 and 0.5, but it's not. The original number that we actually subbed in was 1.5. So don't be fooled and use the number that x minus 1 worked out to be. In this case, it won't make any difference. But, well, no, it will actually. Yeah, it'll make a lot of difference. Okay. So we're going to have to choose our psi again. But when we investigate this function, regardless of what n is, I mean, we know that n has to be bigger than 4 because the fourth one before didn't give me 6 decimal place accuracy. Regardless of what n is, that's a decreasing function. And so this is largest for smallest psi, i.e. largest for psi equals 1. And so therefore, the absolute value of the error at 1.5 is less than (1) to the n plus 1. Okay. This equals doesn't mean that that is equal to this, it means that that's equal to this. Okay, so this is where we are. We are at this point. And so we have been asked, what does the n have to be to make this less than, better than 6 decimal place accuracy? Okay. So if we can make this number better than 6 decimal place accuracy, then this one's guaranteed to be better than 6 decimal place accuracy because it's less than this number. That's what we're doing here. Okay. I'm even going to just... Okay. So we need to know what amount of error goes with 6 decimal place accuracy, and I almost always get this wrong. So I have to reason about it in this way. To the nearest whole number would mean that if it's above a half, you'd go up, and if it's below half, you'd go down. And so to the nearest whole number if I was rounding to the nearest whole number, anything between like 2.5 and 3.5 would round off to 3. And so if my error was less than 0.5, that would give me 0 decimal places of accuracy. That's how I think about it. So, but there's another way. So I just know this. If I had a whole number, just as an example, so this is what I'm thinking to get this right. If I was here, and 2.5 and 3.5, these would all round off to the nearest whole number like that. And so nearest whole number is 0 decimal places of accuracy, goes with an error of 0.5, like that. And 1 decimal place of accuracy would be more like this, right? And these would round off to that because we'd get the first decimal place right. If the second decimal place was between, 2.45 and 0.35, we'd round off to the first decimal place to get a 3, which is the one we were thinking of. So 1 decimal place means that the difference is 0.05. And the pattern continues, so we have no decimal places has no zeros before the 5, and 1 decimal place has 1 0 before the 5, and therefore continuing 6 decimal places of accuracy. Goes with the error being less than 0.123456. Yeah. Which is in fact 5 times 10 to the minus 7. Okay. I always get that wrong, so this is how I think about it, and I know it's sort of stupid, but that's there you go. Okay, so if if this number here is less than 5 times 10 to the minus 7, then the error will be less than 5 times 10 to the minus 7, and we'll have 6 decimal places of accuracy. So we need 0.5 to the n plus 1 over n plus 1 to be less than 5 times 10 to the minus 7. And I have to solve that equation, which is a bugger. Like this would be fine. I could use logarithms to solve the equation without the n plus 1, and that would be fine, and it could tell me exactly which n is the right n. This, not so much. However, with this, if I could find the right n that went with that, then I'd know that I would actually not need quite as big an n because I'm dividing by something as well, and that would make it even smaller. So 0.5 is already about 10 to the minus 1, so probably to the power of 5 would do a good old trick. But then dividing by the 5, so the n would be 4. Dividing by the 5 would make it even smaller, and so I probably don't need to go quite that far. So seems like up to 4 is about where it is, and the quickest way to do it when there's only 4 options to choose from is to just try them all. I will go to my calculator. So 0.5. Oh, come on. So when I go to n equals 2, n equals 3, n equals 4, still not there yet. My estimate was totally wrong. 5, 6, getting there. Oh, my estimate was totally bad. Oh well. Nearly there. Wow. Aha! Not quite. There we go. We're under. We're under 5 times 10 to the minus 7. Sweet! Okay. So trial and error, n equals 7 is the first one. 16, crap. Making up crap, aren't I? I was looking at the 7 and the power. And okay. There we go. And it's okay to just say trial and error. It's fine. I do want to see, just as a quick check. I just wanted to check. So ln of 5 times 10 to the power of negative 7 divided by ln of 0.5. It's 20. Okay. All right. So if I hadn't have had the n plus 1 on the bottom, I would have gotten n is greater than 19 using logarithms. And so I probably should have done that properly, and then I would have expected to do something near the 19 and start there and work my way down rather than starting at 1 and working my way all the way up. Yeah. Okay. Cool. How are we feeling?
It's sort of like the last half is a bit...
Yeah. You watch it again.
No, like specifically with this question, like the
Oh.
last half of it.
The last half? Where?
Sort of like you start picking your thingo number
So you're okay up to here?
back a bit.
How about doing the derivatives?
Yeah, I'm good with the derivatives.
All right, and then putting the n plus 1 in here?
Yeah,
Okay.
it's a bit more.
All right. So I did that in my head because I've done it a lot. But if you want to avoid making mistakes there, literally put brackets n plus 1 instead of every n and calculate it. Because this formula is supposed to matter whichever work no matter which n I'm up to, so it should work for n plus 1 as well. The other option is to think, well, my n went up by 1, so all of these places where n is has to go up by 1. This n minus 1 goes up to n, this n minus 1 goes up to n, this n goes up to n plus 1. Everything goes up by 1. And then this is the formula for the error, just from the notes. And then I replaced this bit with that. This bit here got replaced with that because it was here. Yeah. And then I cancelled the n factorial and the n, plus 1 factorial. And then I did the absolute value, which made the minus 1 go away. That was at this point here. And then because they asked in the very original question a couple of pages ago for 1.5, I substituted 1.5 into this formula just here. And 1.5 minus 1 is 0.5. And then the last thing I need to do to be able to do this is figure out what the psi is. And so I need to imagine if I move psi between these numbers, how does the answer change? And so most of the time I think if psi got bigger, because it's on the denominator, that would make the final answer smaller. Because when you divide by a big number, the answer is smaller. And if psi got smaller, that would make the answer bigger. And I need to find the biggest possible result. And so I choose my psi to be as small as it can possibly be, which is 1. And so I replace the psi with a 1, which gave me this. And then I had this formula. And this I had to arrange to be less than 6 decimal places of accuracy. And I can never remember that. I know it's 5 times 10 to the minus something, and it's 5 times 10 to the minus one more number than the decimal places accuracy you want. Because if you need it to be accurate in the 6th decimal place, then you need the 7th decimal place to be under 5, so that it doesn't round up to the wrong number. Yeah. So there you go, that's how it's done. So after that, the best thing is to just try as many n's as you want to get until it gets under the goal you need. So I just kept trying n equals 1, 2, 3 until I got to a number that was less than 5 times 10 to the minus 7. And the first one that worked was 16.
What does 16 do? Like?
16 means, so I need the 16th Taylor polynomial to estimate ln of 1.5 with 6 decimal places accuracy. Yeah. And in fact, that's a very good point. It's probably an extremely good idea to summarize your final answer like this so that the person who's reading it knows when you've finished. And also so that people who are watching, other friends who are watching it, know that you've reached the goal you're aiming for. Yeah. So we'd actually have to go to the 16th Taylor series, Taylor polynomial, to do it accurately. All right, my recording is going to last for another about 15 minutes, and there was one more thing I wanted to say to round this out, and I'm not going to not say it because this is the best Taylor series seminar I've done in many a year. So, okay. So that error thing just takes some getting used to. There are other examples in the past revision seminars of dealing with errors, and I would recommend looking at them, but I would recommend even more giving things a try. Find as many examples as you can of questions that you have to solve and try them, and also just, well, you can pick ones off the top of your head, and Wolfram Alpha will actually tell you what the Taylor polynomial is for something, and you can use it to calculate whether your error seems about right. Note that errors calculated this way will often, those estimates are much bigger than the error really is usually, because you've been pretty vague about exactly which psi to pick. Okay. The last thing I want to say goes back to option number 1. Like we've been investigating here at the moment option number 2, which is, well, your function isn't really a polynomial, so when we try and pretend it is a polynomial, there's an error and we have to deal with that. Well, option number 1 was, well, it's not really a polynomial, so we'll just go forever and use all of the infinitely many polynomial terms that we could have, and then it will be equal to what it is. And those things are calculated using this reasoning. So this reasoning here, where you find the nth term, when you want the whole infinite Taylor series, you just whack a big sum sign, and that's the Taylor series. So what I want to do is write down the classic Taylor series that you are expected to just know without figuring out. So just so that I can have it in the seminar. So these classic Taylor series are all Taylor series with centre 0, just so you know. And you should know that if you have a Taylor series with centre 0, it's sometimes called a Maclaurin series, because when Maclaurin did this at around the same time as Taylor, he did it with just 0, apparently, I think. Anyway, someone decided that he needed glory, and so we call the ones with centre 0 Maclaurin series. So. Just in case you're Googling things, and it says Maclaurin series, you want to make sure that you don't get freaked out when it calls it that. Yeah, centre 0 is called a Maclaurin series. Okay, so these are the classic Taylor series with centre 0, like Maclaurin series for your classic functions, e to the x. With x to the n over n factorial. And this is just the long version, you know, x plus x squared on 2 plus x cubed on 6 plus and so on. I mean, that's what that means. And you do it forever, and it's equal to e to the x. And what this means is if you do all the derivative things, you know, you find the nth derivative as a formula, and you divide it by n factorial, and you sub in x equals 0, and then you do that coefficient, this is what you get. Sin x is the odd ones from e to the x, but they alternate between plus and minus. So I'm just going to write the long version first. Like that. So sin x starts at x, and it has all the odd powers from e to the x, but they alternate plus and minus. And the shorthand version of this is this. So what it has is that instead of saying, you know, n equals whatever to and only the odd ones here, we go, well, 2n plus 1 will always be an odd number if you put a whole number into it. And so you start with 2 times 0 plus 1, which gives you just x to the 1. And they alternate between plus and minus, which is why there's a minus 1 to the n. And they divide by this power factorial. Sorry? And just to be sure I've got it right, I sub in n equals 0. I'll get minus 1 to the 0, which is a plus 1, x to the 0 plus 1, which is x to the 1, and 1 factorial. Yes, that will produce this answer just here, so it's correct for the first one. Cos x is the same, but the even ones. So it starts at 1, and then it has the even powers. Like that. And the shorthand version of that is this. So it has the even powers, which is why it's got a 2n here. You divide by the matching factorial, and you have minus 1 to the n, so that when n is 0, you get x to the 0, which is 1, and minus 1 to the 0, which is also 1, and 1 times 1 is 1. Yep. Okay. So I always, when I write, I can never remember this version off the top of my head, but I can remember this. That sine x starts at x. And that's because when x is really small, sine x is approximately equal to x. So sine x over x is 1 for when x is 0, approximately 0. And when x is 0, cos is 1. And so if I sub 0 into all of these, I should get 1 as my answer. So, all right, so those are the three classic ones. And there are two more. I should say, while I'm at it, just because I feel like saying it, but not because they expect you to remember it, that sine and cosh, the hyperbolic trig functions, are the same as sine and cos, but without the minuses. Just so you know, in case you were wondering. So yeah, cos and sine have the alternating plus and minus, but if you just make them all plus, it's sine and cosh. Because sine and cosh are the unique odd and even functions that you can add to get e to the x. So, yeah. Okay. All right, there are two more that don't feel like Taylor series, but you've seen them. One of them is this function, 1 over 1 minus x, and that is the geometric series x to the n. You should note that these ones up here all work no matter what x is, but this one will actually only be equal to that if x is less than 1. So. Only if the absolute value of x is less than 1. I mean, weird crap happens when x is equal to 1 because you've got 1 divided by 0, so you don't want that. Okay, so that's the Maclaurin series for 1 over 1 minus x, which is, as you note, the geometric series . Okay, and there is one more, which is this. Maybe I won't put a K, I might put a capital N there. This is the binomial series. Like this, well, this isn't a series at the moment. So if n is a whole number, this is a polynomial. And we already said right at the beginning that if you want the coefficients of a polynomial when you expand it out, you can use derivatives, the same way you do with Taylor series. And that's what this is. But what we're going to do is we're going to take the notation that we use for expanding this out the short way we are going to create a notation for the correct coefficients, and we are going to apply it to any n. And so it's like this. Like that. Okay? This needs talking about. Okay. Right. Yeah, this needs talking about. So this symbol is read aloud officially as the binomial coefficient, the little nth binomial coefficient for big N. Okay, so it's the binomial coefficient with big N and little n. I don't even know how to pronounce it properly, but use the word binomial coefficient. But most people pronounce it aloud as n, big N choose little n, with the word choose. But that reading aloud as choose will only be correct if big N is a whole number. Okay. So I'm going to write all that down. The way to calculate this thing is to have n on the bottom multiplied all the way down to 1. That's n factorial on the bottom. And then what you will do is you will have the same number of factors on the top, also descending, starting at n. Times n minus the appropriate thing. I don't even care what that is. N minus the right number of things so that there are the same number of factors on the top and the bottom. I believe it's little n plus 1. Minus 1, little n minus 1. Because you didn't take off any here, and you need there to be n total. So you take off 0, you take off 1, you take off all the way up to n minus 1, and then there's n things that you've taken off. Same number of factors, top and bottom. Okay, that's what this is. So if big N is a whole number, this will be the number of ways to choose little n things out of big N. So if that's a natural number, then equals number of ways to choose this many things out of that many things. But it totally does not mean that if n isn't a natural number. If n is like a half or minus 7, it does not mean that at all. What we've done is we've just created a formula that will do all of the derivatives and factorial things that we need to find the Taylor series. So remember, when you do a Taylor series, you differentiate powers of x, and you'll multiply by the current power and put the power down by 1. Multiply by the current power, put the power down by 1, multiply by the next power, which is 1 less, and put the power down by 1, multiply by the next power, which is 1 less, and put the power down by 1, and keep going. That's what this part is. So let me just calculate a few of them. 7 choose 3 would be 3 times 2 times 1, 7 times 6 times 5. The 3 times 2 times 1 is always the same for the bottom. And then the top will have, there's 3 factors on the bottom, so there'll be 3 factors on the top, and they start at 7 and work their way down. Which is whatever it is. I don't know what that is. That's 35, actually. I do know what that is. Negative 4, in inverted commas, choose 2, we'll have 2 times 1 on the bottom, negative 4, there should be 2 factors, and I will go down 1 from negative 4. A half choose 3. It's not really choose 3. We're not really doing chooses when we do this. It's just the easiest way to read it aloud. it will be 3 times 2 times 1 on the bottom, because that's always how you do it. And then I will start at a half, and I will have the same number of factors. I will go down by 1 to get minus a half. I'll go down by 1 again to get minus 3 on 2. And now I have the same number of pieces on the top as I do on the bottom, so I'll stop. And that will be, that cancels with that. I think that half and a half and a half would be an eighth, and another times half would be a 16th, and that 3 cancels with that 3. Yeah, and the minus is, yes. Okay. Yes?
With the 7 choose 3, what happens to the 4?
It's just not there.
So why do you stop at 5?
Because there's 3 pieces on the bottom,
Yeah.
so I need there to be 3 pieces on the top. And because I start at 7, I'll go down 1 and down another 1, and then I've got 3 pieces, so I don't need any more. Yep. 7 choose 4 would be the same answer as 7 choose 3. Let me just... Like 7 choose 5 would be... No, I need to do 4 because I'm trying to make a point. So I'll start at 7, I'll go down 1 and get 6, I'll go down 1 and get 5, I'll go down 1 and get 4, and then I'll stop because there's the same number of things on the top as there were on the bottom. And this also comes out to 35 because, well, things cancel. The 4 cancels in this one. Okay. That is what the choose notation means. Technically, you're only supposed to be allowed to read it aloud as choose when it's a whole number on the top, but who cares? Okay, because it sounds fun to say a half choose 3. And you'll notice that 7 choose 8, you'll end up with a 0 on the top, and so it'll come out as 0. Whereas a half choose any whole number will never be 0, because you can't get 0 by subtracting 1 from a half. Okay, so if I'm going to use the binomial series to approximate things, maybe square root of 26, then, right, I'm going to have to make it look like the binomial series. Now, it's actually very important to realise that the binomial series only works when... whoa, what am I doing? If n is a whole number, this will work for every x. If n is not whole number, this will only work if x is less than 1. For n not an integer, not a natural number. Yeah. Just pointing it out. So, here we go. Right, well, the square root of 26 I would need to write somehow as 1 plus something to the power of something. And it's already the power of half. So I could think of it as 1 plus 25 to the power of half. That's 1 plus x to the half. That's great. Only the problem is that the binomial series, if you're not using a whole number power, will only work if this number is less than 1, which is not currently less than 1. So we are going to do a very clever trick, and it goes like this. I'm going to pull out a 25 out of both of these. So this 1 is 25 times 1 over 25, and this 25 is 25 times 1. And now I will do the square root of, well, I can do the square root of 25, which is 5, and now this is 1 plus 1 over 25 to the half. Yay! Now this is a 1 plus x to the half where the x is less than 1. So in all of our other examples when we did them on the screen earlier, the third power was a good one. It got us some pretty accurate results. So that's what we'll do as well. Let's use the third. So use let's use the third Taylor polynomial for 1 plus x to the half centred at x equals 0. And we don't have to calculate that with all the derivatives because we're allowed to use this shortcut. So it'll be 1, it's always 1 at the beginning. And then it will be a half, choose 1 times x, plus a half, choose 2 times x squared, plus a half, choose 3 times x cubed. That's the third Taylor polynomial. Got 4 minutes. Okay, so let's just figure out what those are. Anything choose 1 is always the number that it was, because you have 1 on the bottom and 1 number on the top. So this will be 2 times 1 on the bottom and a half times 1 less than that on the top. And we just figured out what this was earlier, but I will put it in anyway. We'll have 3, 2, 1, a half, minus a half, and minus another 1. So 1 plus, whoa. Okay, so what have we got? Half times a half is a quarter, times and divided by 2 would be an eighth, and it's a minus. And we just figured out that this was a 16th. Okay. And so, yeah, it's probably overkill to go there anyway. And so 1 plus 1 over 25 to the half is approximately 1 plus a half of 1 over 25 minus an eighth of 1 over 25 squared plus a 16th of 1 over 25 cubed. And so 5 times that is the actual answer we want. So whatever the hell the rest of this is. Here you go. So imagine you have a computer that only does powers and doesn't do square roots. This would be a way of figuring out approximately what the square root of 26 is. So it's supposed to be 5 plus a half times a fifth. Whoa, a fifth, David. Minus 5/8 times 1 over 25 squared plus a 5/16 times 1 over 25 to the 3. There you go, it's 5.099. Let's just see. It's pretty good, huh? But imagine that you didn't have a machine that did square roots. This would be, you could do powers. This is good. We got it to 4 decimal places, and we were only 0.0000001 out. So we did really quite well. So that's the binomial series that can be used for that. And the point of it is that you don't have to do all the derivatives. You can just use this mnemonic to help you figure out what the coefficient would have turned out to be. Okay, that's enough of Taylor series, and my recording is going to finish in about 15 seconds. Thank you, everyone.